Jamie Vicary is going to talk about data structures for semi-strict hierarchy categories.
Thanks a lot, Mike. Hi, everyone. Okay, so my microphone's clearly working. I'm going to tell you about data structures for semi-strict high categories. So I'm starting a bit late. I'll try to be as quick as I can. Okay, thanks very much. All right. So this talk is all about higher dimensional algebra. What on earth is higher dimensional algebra? Well, what is ordinary algebra? This is something that we learn from a young age. We arrange symbols in a line. Okay, and these things have some meaning. We could be in any number of different specific settings. We could be doing calculus. We could be doing group theory. We could be doing lots of things. But something we're familiar with is arranging symbols in a line, manipulating those symbols, applying equations, and so on. But there's no reason that we need to restrict ourselves to arranging our symbols in lines. We can arrange our symbols in higher dimensional spaces. We could arrange our symbols in a two-dimensional space, say, a three-dimensional space, or in an even higher dimensional space where things become harder to visualize. So what's the point? Why is this interesting? Why is this rich? Because once you're in a higher dimensional space, suddenly any homotopy, any isotopy of the space in which you're embedding can act on your composite. Okay? So any way that we could take, say, of taking this planar diagram and doing some planar isotopy, we could ask, for example, that this composite we start with and that isotopic composite should have the same interpretation in terms of our underlying structures. So you get a lot of rich geometry and rich connections between algebra and geometry in this higher dimensional setting. Now, where do these pictures come from? Why don't we in fact see these pictures very much in modern mathematics if they're so natural and so important? Well, pictures that we might see, for example, in category theory papers would be pictures like this. This is called a pasting diagram, a picture like this, and the idea is that A, B, C, D, E, F are categories. These single barred arrows are functors, and the double barred arrows, which run vertically, are natural transformations, and they've got names S and T. So this is a pasting diagram. It's very different to the diagrams we just saw before. But if we dualize this diagram, that means everything that was a point before becomes a region. Everything that was a horizontally tending arrow becomes a vertically tending wire. And this thing S, and these things S and T, which are filling in these whole regions, they now label points. What we get is a diagrammatic calculus representation of exactly the same geometrical information. Okay? So the graphical calculus representation is the dual diagram. It's not fundamentally encoding any different sort of information as these more traditional diagrams. And the idea is that in general we would expect n categories to have an n-dimensional graphical calculus. Okay? And for n greater than 2, this is not really a theorem. This is something that, and it's an expectation, it's something that would motivate perhaps our very definitions of n categories. So what's the point of high-dimensional algebra, and what impact does it have? Why should we study it at all? Well, there are a range now of very striking applications, striking in the strong sense that in 100 years people will look back, I claim, on these applications and think, wow, that was a real achievement of 21st century mathematics, or whatever it is. So I would mention here homotopy type theory, topological field theory, and higher topos theory. Right? This guy looks a bit like Mike Zuckerberg. This is Jacob Lurie. He's too cool to put a shirt on, but well, John was too cool to put a shirt on as well in that picture. Okay. And so, I mean, these are just like this, what I think are going to be looked back on as the super impressive, right, epoch-making applications. Of course, there are a huge number of other applications, right? Concurrency, quantum computing, all sorts of things. That's Graham Siegel and that's Michael Atiyah. Yeah, that's right. The people who do homotopy type theory obviously don't put their face on. I could have got their faces as well. There's lots of faces I could have chosen. Okay. But why is this a subject that people think is a bit difficult, right? We're doing science. Lots of stuff is maybe ostensibly difficult. So here's a quote from Jacob Lurie. High category theory is generally regarded as a technical and forbidding subject. So why is this? Why does it have this reputation? Well, even from a relatively simplified perspective, this word semi-strict means we throw away as many of the axioms as we can just to make the system we're working with as simple as possible. A 2 category, that is something with a 2-dimensional notation, comprises 3 sets, 6 functions, and 12 axioms. A 3 category comprises 4 sets, 19 functions, and 58 axioms. A 4 category comprises roughly 5 sets, 34 functions, and 118 axioms. Okay, so it's really horrendous. It's really impossible to even conceive of doing any sort of formal work, certainly in this sort of setting, almost in this setting. And this setting, people just about manage it, right? If you want to formally prove that your theorems are correct, that you're not making any mistakes, if you want to prove, say, that you've really got an example of a 4 category, in principle, you'd have to check all this stuff, okay? And it's really, really horrific. So why can't we use proof assistants to work with these structures? Right? Well, proof assistants like Coq and Agda exist, and they're used in a lot of settings. But the trouble is, of course, these proof assistants just use one-dimensional algebra. They just let you type in strings, one-dimensional strings. Okay. Now, there's no reason at all that we need to restrict ourselves to this. There's no reason we need to restrict ourselves to formalizing compositional concepts with computers only in a one-dimensional way. We're sort of used to this with graphical user interfaces, right, and Windows. Okay, we can arrange things in 2 dimensions. We can use basically the same sort of geometrical ideas in our proof assistants, I claim. So we have a solution to this, myself and my collaborators. It's called Globular. It's a proof assistant for higher category theory, and it's available right now at this web address. If you have a computer, we're going to do a demo, and you could follow along if you would like, if you have Chrome and you wanted to fire that up. So we've been very pleased with the level of success that this has had in terms of people being interested, engaged with it. It's been around for almost a year. My PhD students made me a nice Globular first birthday cake last week, which was very nice. Loaded over 9,000 times by over 2,000 people, right? Now, maybe most of this is me, right? But you can't say most of this is me. I mean, we were expecting 2 orders of magnitude less. We would have been happy with, like, if 20 people had shown an interest in this, right? Okay. So who's behind this? Christoph Barr, my student, Alex Kissinger, who's not here, who's in Nijmegen, and myself. So it has many features which we find to be attractive. Firstly, and very importantly, it runs in the browser. There's absolutely no barriers to use. If you come across a link to some proof in this system, you can click on the link, and then you'll be right there instantly. Nothing to download, nothing to compile, no dependencies to update. You don't need to change your file system of your computer. You don't need to reinstall your kernel, right?
You need to know what n categories.
You just need to know what n categories are. Okay. Yeah, precisely. So of course there's a syntax, but it's not a syntax that we're familiar with from something like Coq and Agda. It's because it's a higher dimensional syntax. So we interact with it just by clicking and dragging and using the mouse. One can generate images with this thing to use in one's paper. There are many people many people in this room, and many people not in this room, write papers full of pictures. These pictures are supposed to be formal objects that explain or account for the results that they're presenting. But how are these pictures produced? Well, just with something like Photoshop or something, right? Or some vector graphics package that is not a formal object. These are not pictures being produced by some proof assistant, usually. They're just pictures being produced by something that knows what a pixel is, and it knows what it means for a pixel to be one color, not another color, right? If there's some mistake in this picture, right? There's no plugin to Photoshop, which if you make some mistake, you misapply one of the axioms of 4 categories in your Photoshop diagram, right? Photoshop isn't going to pop up a little note, right, and tell you you're doing the wrong thing. What if you change your proof strategy? What if you want to simplify your proof? It's extremely hard. So we can get around lots of those problems here. But even better, right, even better than downloading images using your paper, include a direct link in your PDF so people can click. They'll be taken straight to your proof, and they can interact with it. They can scan through it. They can explore it. They can even change it. They can try and simplify it. Okay, and this supports proofs up to the level of semi-strict 4 categories, so 4-dimensional composition. So that's pretty high. It's already beyond the level at which these things become really easy to visualize. So the computational support is something that's helpful in those sorts of dimensions. Okay, so time for a demo. So I'm going to switch to my browser, and I'm going to go to globular.science. So here it is, and I'm going to go full screen. So Globular works with presentations of higher categories. Okay? So you give the building blocks for the structures you want to build. Then Globular helps you glue them together. So all we start with is a single zero cell. It's called cell 1. We can change the name of our structures. So if I turn my mouse on, that will help. So let's call this cell A. We can also change the color. Okay, there we go. I spent a long time choosing nice, soothing initial colors. That's my favorite shade of blue. Okay, so what can we do? Not very much. All we can do, well, one thing we can do is create a new zero cell. So here's a new one. Let's call it B. Now, we can't really compose anything yet because these are just zero cells. They're objects. They don't go from anything to anything. We can't really do anything with them yet. So what we need to do to get some notion of compositionality is we need to construct some one cells, some morphisms. Okay? Now, in this system, an n cell is defined by precisely two things. Its source n-1 diagram and its target n-1 diagram. So we want to build a one cell. So we have to give a source and a target. So we can break the symmetry here. Let's click A and choose for it to be the source. So we click source over here on the right, and then it comes down there in the corner, so we remember what we're doing. Now let's click B. Now let's click target, except I can press T on my keyboard. You see there's a little underlined T, so I can press T. So now we've got this thing called cell 3. We can click on it and it'll come up large, and we can try and understand why has it drawn this picture to represent cell 3. Well, the idea is this. We start over here with A. You see it's blue, and if we move our mouse cursor over the picture, it will show us what we're looking at. So here's A. Okay, now as we go along, we've got A, we've got A, we've got A, we've got A. Cell 3 happens, and now we've got B, 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 B. Okay, so cell 3 exists to do nothing more, nothing less than turn A into B. And so over time, we get this sort of trace. Cell 3 happens in the middle, time 0, if you like. Okay, so still we can't do any composition because cell 3 goes from A to B, so we can't compose it yet. So let's make another one cell. Let's make something going from B to A. So I click B, I press S, I click A, and I press T. So now I've got cell 4 as well. Cell 4 has got the opposite type. So now we're ready to do some composition. So let's try this. Let's start the compositionality. Okay, so I'm going to click cell 3, and this will come up large. This is the current diagram that we're building, and I want to attach cell 4. So I'll click cell 4, and I'll be told there's two ways to attach it. I can attach it on the left here, on the right. And it's checking the types, you see, and it's seeing that both of these are possible. Because here we're blue on the left, and cell 4 is blue on the right, so we can attach it on the left. And here we're red on the right, but cell 4 is blue on the left, so we can indeed attach cell 4 on the right as well. So it's giving us both those options. So let's choose one of those. Let's choose this one. Now this is a composite diagram. It's not one of the building blocks on the left. It's a non-trivial way to connect those together. But now we can use this as the source of a 2-cell. So let's click source. Now for the identity, for the target of this 2-cell, I have to choose another 1 cell. So I've clicked A here. I can't choose this. This is a 0 cell. But I can click identity over here. And this will give me the identity 1 cell on A. So this is like A just existing over time. And now I click target. And now we'll have a source and a target for a 2-cell. So we'll construct that 2-cell. And here it is. Let's call it cell 5. So what on earth is going on here? There seems to be some richness here. How did it know to draw this picture from the information that we gave it? Well, first, let's understand where that source and target are living inside this diagram. So remember, the source was cell 3 and then cell 4. Cell 3 turned A into B, and cell 4 turned B into A. If we read along the bottom boundary of the picture, that's exactly what we have. We have A, cell 3, B, 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 cell 4, A. So that source that we specified is drawn along the bottom. It's the bottom boundary. What about the target? That was just the identity on A. And indeed, that's what we can see along the top. So how has it drawn this picture? Well, it's taken the cone over the bottom boundary and squashed it into a point. It's taken the cone over the top boundary and squashed it into a point. The top boundary just shrivels, so you can't see anything. And instead of drawing these as straight lines, it's drawn them as sort of arty curved lines to make it look a bit more graphically sophisticated. And then it's just drawn a blob in the middle to patch over this singularity where all the cones were joined. And it's called this blob cell 5, which is what we called this two cell that we've built. Okay, so now what we're going to do in this demo is we're going to look at the idea of an equivalence. And we're going to prove a non-trivial theorem involving an equivalence in a 2 category. And luckily, this is part of the data that we need. So I'm going to build the rest of the structure a little bit faster than we were going before, using the keyboard shortcuts, if you sort of know. And this is where I said if you can follow along. Sorry, it's a bit tough because I'm now doing it at super speed. So here we've got 3 more 2 cells, just the different colors and the different orientations of that thing we just had. But now for an equivalence, we also need some additional rules. So let's just change the names a bit so it's a bit easier to see why this is something called an equivalence. So our 0 cells are going to be called A and B. My 1 cells are going to be called F and G. And let's call these alpha, beta, gamma. No, she's a logician. She's not here. Delta. Okay, delta. All right, so let's look at something like gamma. So why is this part of something called an equivalence? Well, the idea is that we can think of A and B, the blue and red regions, as categories, and F and G as functors that go between these categories. And these functors are supposed to be witnessing the fact that A and B are equivalent categories. Okay? So if they're equivalent to each other, then what does that mean? What's this structure gamma that we've built? Well, along the bottom, we start at B, we pass to A, and then we pass back to B again. Well, if A and B are equivalent, then why did we bother doing that? We could have just stayed at B all along, and it would be the same. Okay, and this process gamma is a process that says if you do this complicated thing, start at B, go to A, go back to B again, you may as well have just stayed at B all along. And we have all the different variants of this rule.
Why don't you click invertible and gamma?
So that's an advanced feature of the tool. If you click invertible, then it generates a lot of structure, which is just the structure I'm putting here by hand. So I don't want to use those baked-in things. I want to do it manually. Okay, but now we can compose in higher dimensions. Before we did composition along a line, but now these tiles are 2-dimensional, so we can compose in the plane. And we do that just by clicking. So I want to perform a composite here. I've got alpha. I'm going to click down here. And it will tell me everything that can be attached. Beta can be attached and gamma can be attached. And if I move my mouse cursor over, it will show me where they attach. So beta, I can plug into the bottom there. Gamma, I can plug into the middle there. If you look at the types, then that makes sense. So I'm going to attach beta at that point. So here we start at A, and then we pass to A, and then B, then A, then we pass just to A again, and if we're going to do all of that, why didn't we just stay at A the whole time and not do any of this if A and B are equivalent categories? So this is still part of the definition of an equivalence. If I can do all of this, then I may as well just have the identity on A the whole time, okay? And then there are a few more variants of this that we can build, which I will build again at some speed. Right, it's a bit hard to see what I'm doing because all the cells I'm creating are off the bottom down here. So I've created some of these guys. Okay, so this is the target. Okay, and I'm going to do it with the color reversed. Right. So now this is all the data that specifies an equivalence. It's literally just a graphical transcription of the definition of an equivalence between categories that you might find in a textbook on higher category theory. So now we're going to prove our theorem. Our theorem is the following, stated in sort of traditional terminology. It says that any equivalence between categories gives rise to an adjoint equivalence. So an adjoint equivalence is an equivalence that additionally satisfies the following equation. So let's build it up. So we're going to start with alpha here. I want to attach a wire on the right, so I'm going to click near the right-hand boundary, and it will attach an F. It knew to attach an F and not a G, because a G wouldn't make any sense to attach there. A G needed a red region on the left, but an F needs blue on the left, so that was fine. I'm going to click here, and I'm going to attach a delta. So to have an adjoint equivalence means that if we have this composite, then we can transform this into the identity. Okay, that's what it means to have an adjoint equivalence, further and above the equations, the structures we've currently got. Now, it is not true that every equivalence is an adjoint equivalence. So it is not possible in this rewrite system to transform this diagram into the identity diagram. Okay, and that's not what the theorem says. The theorem doesn't say that every equivalence is an adjoint equivalence. It says that every equivalence gives rise in a canonical way, in a number of canonical ways, to so let's say non-canonically, to an adjoint equivalence. Okay, so how does it do that? Well, we need to redefine one of these structures, alpha, beta, gamma, delta. So let's redefine delta. So we're going to redefine it, so we have to produce something else that's got the same overall type as delta. So we need the same lower boundary and the same upper boundary, but we can make the diagram itself be more complicated. So let's do some attachments. I'm going to attach beta up here, and I'm going to attach gamma over here. So we've got something that looks like the bottom end of a hockey stick. But if you check the types, it's still got the same overall type as this structure that we started with. Red identity along the top, and red identity along the bottom, and red, blue, red across the top. So now we want to store this. We want to use this as a definition of a new structure. And for that, strangely, we're going to click the theorem button. Why on earth does theorem mean definition? So it's a strange idea, but from the perspective of higher category theory, there's no difference at all between a theorem and a definition. Why on earth should this be? Well, let's try and talk about a theorem in a way that makes it sound a lot more similar to a definition. When we give a theorem, we give a theorem statement, okay? And in this sort of setting, that's always of the form such and such a cell exists with a certain type. And then we give a proof. Well, that's just showing how we can actually instantiate, we can actually come up with a witness of something of that type from the basic structure. But that's just the same as a definition. It's just the same as we're going to define a new structure to be a given composite of our existing structures. And then the overall type of that structure that we're defining, that is our theorem statement, if you will. So when I clicked theorem, it produced two new things: a new tile, a new two-dimensional tile with the same type as delta. So we could call that new delta. And then down here, it constructed a 3-cell that tells us the definition of new delta. It tells us how to transform new delta into a composite of our original structures. So now we can try and prove that this family where we throw away delta, but we instead keep new delta, is an adjoint equivalence. So let's have a look at that adjoint equation. So I'm going to build the same equation that I did before by clicking in the periphery of the diagram and choosing from the list to disambiguate when there are multiple things that can be attached. So now here's the snake. We're going to show that this can be rewritten into the identity. So what's the first step we're going to do? Well, the first thing we're going to do is tell Globular that we want to remember everything that we're doing, because this is the proof we're going to construct now. We want to remember all the steps of the proof. So we don't just want to transform this 2D thing into the final 2D thing. We want to remember the whole sequence of 2D steps. We want to construct a 3D proof object. So for that, we click the identity button over here on the right. And we'll talk a bit more about that later. So now, what's the first non-trivial proof step? Well, we're going to substitute in the definition of new delta. So for that, we click. There are a few things that can be done in this region. We're going to apply the definition of new delta. So now we've got this. Okay, it looks pretty bad, okay, because we said that, so this is now all in terms of our original alpha, beta, gamma, delta. Now it looks pretty bad. It looks worse than before, because we said that whenever we had a single little snake composite, we couldn't rewrite it into the identity. And now we've got two of them, one inside the other. So how can we rewrite this into the identity? Well, like lots of complicated sort of non-trivial proofs, we have to make this more complicated before it gets simpler, before we turn it just into a single straight line. So the first thing we're going to introduce is a little red bubble over here in this blue C. So I could do that by clicking. I could also do it by choosing the move that I want. So I want this move. This move introduces a red bubble in a blue sea. So I'm going to click here, and then Globular will tell me all the places where I can do this. If I move my mouse over, then those highlights come up large. I want to do it about here. Okay, so now I want to cut through these two walls here. So where's the rule for that? It's down here. I click here, and it shows me everywhere this applies. I want to do it here. Okay, now we can start to apply some isotopy to this diagram. This is the whole point of higher dimensional algebra. Isotopies of the plane act on algebraic structures. And in Globular, the idea is that this is visceral. You reach out, you grab a node, and you pull it up or down. So this blue node here, I want to drag it down. So I click and drag. This blue node here, I want to drag it up. I click and drag. Maybe I do it again. Now this is a bit more interesting. Here we've got delta facing off against gamma. Delta could be pulled down to the right or to the left. Both of those would be topologically permissible. And you do that by dragging at a certain angle. So if I drag down delta down and a little bit to the right, you see it'll go down here. I can drag it back up again. I can drag it down and a little to the left. Okay, so let's keep sort of playing around. So why are we playing around? Well, maybe, as is often the case in high category theory, you don't know how to prove the thing you're trying to prove, or you don't even know if it's true, right? You're doing exploratory mathematics. This is, of course, always the case in science. So that's the first role that this tool can play, helping you to explore and play around with a set of algebraic structures to see what's possible. Okay, so we don't know what we're doing. We're playing around. But then we notice we can do something a bit interesting here, because gamma and delta, we can apply a rule to sort of cancel out this gamma and delta. So I click here. And let's see, there's lots of things that apply. I can find the one that here. This just involves that gamma and delta. So I click this cell 15, and then it annihilates. Now let's do a little bit more rearrangement. Now we see here this might be a good place to apply an operation. Here, cell 15. Okay. And now we're doing pretty well. Now all we're left with is two red bubbles. And we know that we can kill red bubbles, and we'll just get the identity. So let's find our rule that lets us kill a red bubble. Here it is. If I click this, nothing comes up. There's no matches. It's not letting me apply the rule. Why is it not letting me apply the rule? Because the matching algorithm that it's using is absolutely exact. We have to literally see this exact little tile as a subdiagram of our main image. And we're not seeing that, right? These red bubbles are too tall because this critical point here of this other bubble is interleaved with these 2 points. So we've got to fix that problem first. There's many ways we could fix that problem. For example, we could sort of pull this up here. And now we can kill both of these red bubbles. So if I click here, it'll tell me this rule matches in 2 places. So we choose one, and we choose the other, and we're done. We've rewritten from the snake to the identity. So we've proved our theorem. Now, that was great. So the first thing we would ask is, what on earth did we do? Okay? Maybe we were doing something far more complicated than this. What on earth did we do? Well, we can see what we did, because you might have noticed this slice command has been incrementing as we've been going. So if we change the slice command, we can see everything that we did. And we could look through that, and we say, oh yeah, that bit where I just put these guys up and down, that was pointless. That didn't help me achieve my goal. So you could look at that, and you could learn from it, and you could try and do better next time, construct a more efficient proof. But something else that you can do is visualize this proof in a completely different way. So as I've already alluded to, here we've got 2D slices. Each stage of our proof is a 2D slice. We could imagine printing out these slices and literally stacking them as pieces of paper one on top of another. What we'd have in front of us would be a 3D object, a stack of 30 sheets of paper. Okay, one way to visualize that is like a CAT scan, right, to slice through it. Another way to visualize that is to look at it from the side and imagine what would be the effective 2D picture that you would see from the side. And what you'll see is as each of these vertices move up and down in the slices, from the side, these points trace out world lines that move around and interleave each other. So what we want to do is project out the third dimension. We do that with the project control. So we go up here. At the moment we're projecting out 0 dimensions. Instead we want to project out 1 dimension. And we get this image. It's a single image that represents our entire proof. And it looks a bit like a knot. Well, why is that? Well, knots are bits of string embedded in 3 space. Here we've got rewrites embedded effectively in 3 space. And it turns out that, topology and algebra are closely related, as you might have heard, right? This is just an instance of it. Now, this is a bit more complicated than the diagrams we've seen before. So we can use the zoom feature. We can use the scroll wheel on our mouse. We can move around. Each of these lines are now alpha, beta, gamma, delta. The lines are now the things that used to be vertices, because now we're seeing the world lines that these algebraic structures are tracing out over the course of the proof. And now, inefficiencies in our proof become absolutely clear. Here, we braided this green strand over the red strand and then back again. Okay? Topologically, this isn't helping us achieve our goal, which is sort of right at the top. So we can cancel it out. How would you eradicate this? How would you get rid of this if you were really looking at bits of string in front of you? Well, you put your finger in here and slide it down and tease the strings apart. So that's exactly the user interface mechanic that we have here. We click, say, at this crossing, and we pull it down, and it will cause them to cancel out. So what else can we do? So we can manipulate this as a 3D entity, albeit one that we're seeing in a two-dimensional projection. So we can also pull things up and down, just as we could before. But now in 3D, there are new types of isotopy that are allowed. So here we apply a move, and then we cross both these strands over the blue strand, right? We may as well have just only bothered applying this move on the other side. It would be much simpler. And to do that, we grab this pink vertex and we pull it up, and it will move it across. Okay? So in this way, we can affect all sorts of simplifications of our proof. Okay? And I'm not saying, all right, here we can pull this down, we can pull this down, we can cancel this out, we can pull this up, we can cancel this out. You can do all sorts of stuff. Okay, now let's say we get it into a state that we're happy with. What about the original 2D slices, right? Where have they gone? Because that's the actual full detailed content of the proof. Well, it's all still there. We were manipulating our entire proof as a 3D object. We can just revisualize it now in terms of the original 2D slices. So we set project to 0. And now we can see a far more efficient proof. Well, that wasn't very efficient, was it there? We obviously didn't finish the job. But this proof is only 18 slices long. It was 30 before. Okay? So I hope you see from this demonstration the point of Globular. You can build up an algebraic system. You can work with the components. You can play around with trying to construct proofs. You can simplify your proofs. And now, if we wanted to, we could publish this. And then the Globular server would assign this a permanent sort of archival number, a bit like the archive. And then you could use that as a permanent URL to link from your research paper. Okay, so let's just talk in a few minutes to finish about the theory. What's going on here that allows this to happen? I think it fits in nicely with this description of semantics that we've had this morning. So 2 words, signatures and diagrams. A signature is a list of allowed moves that we're going to have in our category. It's the generators of our high categorical structure. It's all the stuff we have down the left-hand side of the tool. A diagram represents a generic composite of moves. It's a way to fit together lots of moves into a single composed structure. So this is an example of a diagram, okay, of the sort we've seen before. Now, a crucial point, this was one of the greatest insights I think that we had as a team in producing this tool, is that we only work with diagrams which are in generic position. That means we never have 2 vertices at exactly the same height. Now, if you're doing category theory on paper or you're looking at research papers, you will often see multiple diagrams at the same height. But we don't allow that, and it allows us to use an extremely simple data structure to encode this diagram. Let's see what that data structure is. How do we encode this 2-dimensional diagram? Well, the first thing we do is we encode its source. Okay? So we do this, and then we do this, and then we do this. We just give a list of the stuff that we do. Okay? So it's just this list. And we just encode that as a list in the obvious way, because these things have all got names, so that's easy. Now, how do we encode the 2-dimensional diagram? Well, what we do is we give a list of instructions. We say, at each height, which 2D tile are we going to attach, and at what coordinate? So if you like, how many wires are to the left of my tile when I attach it to the source? Well, there are no wires to the left here, so we say we're going to do this tile with no wires to the left. Then we attach this tile with 1 wire to the left, Then we attach this tile with no wires to the left. Then we attach this tile with one wire to the left. So this diagram is encoded recursively by first encoding its source and then encoding the list of two-dimensional tiles that are used, ordered by the height at which they appear in the diagram in this way. Now, if two tiles appeared at the same height, you couldn't order them. So this list structure would have to become a lot more complicated, and that has a huge number of ramifications down the line, because this basic data structure is what all of our operations are acting on. Rewriting, for example, whenever we rewrite these structures, it's so helpful that they're so simple. So in what ways do we rewrite them? Well, in order to be doing category theory, we need this sense of isotopy which we've seen. So what we do is we identify different fundamental types of isotopy. If we've got alpha, beta here in the plane, we can exchange them. If we've got alpha here above another wire that's in the background, we can slide alpha down. And there's a few more things that we can do. All of these equations, these sort of families of equations, families 1, 2, 3, 4, and 5, these are all well known, these are well understood in the category theory literature as being important. These are the ones that we use. And then we could use this to give new simple definitions of higher category theory. We can say that, if we say that an n signature is just a signature, a list of rules, which is at most of some dimension n, then we say a semi-strict 2 category is a 3 signature that supports moves of type 1. A 3 category is a signature supporting moves of types 1 and 2. And a 4 category is a signature supporting moves of types 1, 2, 3, 4, and 5. So in this way, we get a concrete definition, say, of semi-strict 4 category, which is vastly simpler than existing definitions, which, as I said before, something like 70 requires, to define a semi-strict 4 category traditionally, you have to give something like 70 functions and check they satisfy 140 axioms. We've reduced that by an order of magnitude. How have we done that really? Well, because we're not trying to give a syntactic definition of a semi-strict 4 category, we're doing it in a semantical way. We're saying here's a very, very, very simple data structure, which allows the axioms of on which the axioms of a semi-strict 4 category or in general a high category to act in a way that doesn't lose any information. So forget about the axioms of higher category theory as conventionally proposed. Just work with these data structures, this very simple list-based data structure, and then you can play with your 4 categories or your n categories, and you can construct formal proofs to your heart's content. So thanks for listening.
Hey, Jamie. So at some point in your proof, you got stuck and you said, I can't do this match and I have to move things around, right?
It's a deliberate mistake, Pavel, I'm sure
I know. But I was just wondering, in Globular 2.0, right, can I have a button that says...
Yeah, maybe. Yeah, maybe.
And that does all these philosophies automatically?
Yeah, because that's not actually... So what Pavel is saying there is that at a certain point I wanted to apply a move, and I couldn't apply the move, but only because I needed to do a little bit of isotopy first. Now, so why couldn't Globular have coped with that for me? Why couldn't it have been a little bit intelligent? So that's absolutely the sort of thing we want to do. So I've called this a proof assistant, but really it's just like a clever piece of paper. It doesn't do anything for you other than storing the structures that you construct. But once you've got that as a foundation, it's fully formal, and you can have tactics, and you can have these automated techniques. So in particular, because of how isotopy is formalized in Globular, the space of isotopies of a particular diagram is always finite. So you could certainly write some procedure that would just that would scan through all those possible isotopies, and you might have a huge number of matches, which would be very useful, but sometimes you just have a small number of matches, and that would really help you find your proof.
Oh, well, yeah, I mean, you could probably do, it will be like factorially big to find, all number of isotopes, so you can probably just do some kind of canonicalization representing things as graphs with orderings on vertices.
Right, so that's right. There's another data structure you can use which precisely identifies 2 diagrams just when they're isotopic. And that's actually an extremely simple procedure, but the trouble with that, it doesn't help you with the problem of matching. Because matching is ill-defined in that case with few quotient by isotopy. Because as we've seen, right, it matters exactly how you lay your diagram out, whether or not there will be a match. So that's the problem that's introduced.
Ross?
So is it fair to say, Jamie, you've achieved this great simplification in the definitions of the higher categories by essentially taking all the complexity that was there and stuffing it into the search problem of finding proofs in the first place?
No, I don't think that I don't think that was the complexity that was in these axioms we've thrown away. Huge numbers. So what on earth are these 140 axioms? Well, in a 4 category, you've got 4 ways you can compose in 4 dimensions, and all those compositions are associative. All those compositions are unital. We throw all of those axioms away because we represent everything as a list. A list does have associative composition. It's a theorem about lists, not an axiom, right? Lists do have strictly unital composition because if you concatenate a list with the empty list, you get back the list you started with. That's not an axiom, that's a theorem that you could prove if you want to. And indeed in our paper, that's where the theoretical work is here. We don't have any proofs saying that this definition of semi-strict 4 category that we get agrees with any previous definition, but we have lots of really non-trivial theorems, at least the proofs that were hard to find. We found the proofs hard to find, and the proofs are quite long, showing that huge numbers of properties that in traditional approaches to category theory are axioms come out now as theorems. And we go to a lot of work proving those theorems to give confidence in our approach.
So you want to prove that you get no more than those?
Right, we haven't got a proof of that.
Yeah.
Right. Yeah.
Do you have a guess for what semi-strict 5 categories in your approach?
Yeah, so semi-strict 4 category is really kind of nice because there was only one previous definition of semi-strict 4 category, and it was a bit sort of rubbishy, right? I mean, it's very impressive for what it was, but really if you're going to list 140 axioms, it's quite hard to do it in a tidy way without making any mistakes. And it was quite old work, and there are some of those homotopy moves I described weren't sort of known about then, so there's some stuff there that's missing. But yes, we have a systematic way of understanding, well, in fact, I mean, it's only through talking to John that I discovered this. He's planted this question so I could say, yes, you don't. I'm kidding. Okay. So there are beautiful high-level ways of understanding all the different ways you can compose stuff. So here, this is just saying so why does this move exist? Well, really it exists because we might want to have alpha and beta at exactly the same height. We're not allowed to have it exactly at the same height. So the next best thing is to have moves that go between the 2 ways of breaking the symmetry. Here, why does this move arise? Because we might want to have alpha exactly in front, this wire that runs behind it. But that's not allowed in this system because it's generic. So the next best thing we can have is a move that lets us go from this way of breaking the symmetry to this way of breaking the symmetry. So in other words, all of these axioms arise from disallowed compositions. And these disallowed compositions, it's well known combinatorially how to list them all using these things called Batenin trees. So we can just list all Batenin trees of a certain class, and then they give us all these moves, and then in principle we could implement them. But I mean, it gets a bit horrific, and you have the fundamental problem that if you want to do n categories, there's no finite amount of programming that will get you to infinity categories, right? Because you have to handle each case by hand. Each dimension, there's more stuff. So, I mean, we're going to do something better for 2.0, yeah.
Any support for linear categories where our morphisms are vector spaces or something?
So this is all purely geometrical. There's no support for anything like that. But it would be great to have a way to take some composite structure like this and say, well, wait a minute, these wires really represent vector spaces. These vertices really represent linear maps. Or any other sort of structure, of course, because you can use monoidal categories. One could imagine a functor from this syntax into any sort of interesting target category, and then you could ask Globular to do the composition for you, to compose all these linear data, or these function data, or whatever it is, in exactly the way that the diagram encodes. So that's something we'd like to do.
When you introduce a new cell, can both the source and the target be arbitrary composites?
Yes. Yes.
Those moves are reminiscent of knot theory. Is there a connection?
Yeah, so thanks for your question. So what are the applications of this area? Well, a huge application is knot theory. There's a guy called Scott Carter, which some of you might know because he's a knot theorist. He does lots of beautiful work, and he's sort of in the area of descriptive topology. I'm not sure if that's a bit of a rude phrase or not. I should ask him. Basically, a lot of conjectures in knot theory say that this knot is isotopic to this other knot. And there's no real clever way to do it. You've just got to find okay, that's very clever. But you've just got to find the isotopy and visualize it. So a great example is a great example is, let's see. So a great example, if we go to the Globular NLAP page, we've got tons of examples. So there are about 40 public proofs that people have published. So here's a list of some of them. So one here, the Perko knots are isotopic. So what does it say here? The Perko knots are a pair of 10 crossing knots stated by Little to be distinct, but proven by Perko, a grad student at MIT, I think, or somewhere on the East Coast, actually to be isotopic. Okay. Now, apocryphal. The legend goes he was on his kitchen table with some rope that he'd arranged in the form of one of these knots, and he was manipulating it.
Proof assistant.
Yeah, and he was manipulating it. He started laying it out in the manner of Perko's first knot, and then 12 hours later he realised it was now Perko's second knot. They weren't called Perko's first, so maybe he called them that, but no one else called them that at the time. But then what is the first thing that he would think? What on earth, what did I do? Right? What did I do? Yeah, he phones up his supervisor, he says, I've done it. Well, what did you do? I have no clue. If you look at so we formalised this, and it's here, and of course we're running out of time. But it's 250 steps. So this is Perko's first knot, right? And we go through, and we apply the Reidemeister moves. Reidemeister 1, we have to put in by hand. Reidemeister 2 and 3, we don't have to put in by hand because they're just axioms of 3 categories. It's really very simple. Slice 250, this is Perko's second knot. Now, in his research paper that he published in 1974, describing this isotopy, he gives 5 pictures, right, that are supposed to be the descriptions of this isotopy, right? The idea, I guess, that each picture was really like 50 moves in this absolutely fine-grained sense. Because what else can you do? I mean, and it's impressive enough that he managed to capture the whole thing in his head in a way that allowed him to present it at all. With a tool like this, I think it would have helped him. I don't know. Apparently he quite likes when people email him about his isotopy, so I'll do that. Sure. Yeah.
Going back to Turing, there's some unsolvable problems with the knot unraveling.
Right, so often it might be undecidable whether in general, so in general it's undecidable whether 2 knots are isotopic. That doesn't mean that there aren't some concrete conjectures that you may or may not be able to solve.
I think
It's an intersect co-NP.
Yeah.
You're thinking of links maybe, which might.
I'm not sure, but it's hard stuff in general.
But it's not undecidable.
Okay.
Thurston and Hagen came up with an algorithm to tell whether knots were isotopic, or maybe whether or not was the unknot. But it's a very inefficient algorithm. It's not practical.
I see.
So.
Interesting.
Okay, well, let's thank Jamie again.
Thanks for that.